Hello and welcome to my video lesson 3.3 on moving charges in magnetic fields. So since we learned in the last video that a moving charge, a moving electron would cause its own magnetic field to occur, we can use those magnetic fields to interact with other magnetic fields, causing an attraction or repulsion. So to get an idea of what's happening, we use another hand rule, the third hand rule, to do this. So the third hand rule for moving charges, instead of a straight line or coiled wire, it's for moving charges. We use our left hand if it's a negative charge or our right hand if it's a positive charge. Now we can have a moving positive charge, but not in a coil of wire or in a straight line. We have a moving positive charge if we have an alpha particle or a proton or a hydrogen without its electrons. So those are all possible options, but it could be our negative charge, could be a positive charge, left or right hand, respectively. Now the thumb is the direction of the electron flow in this case. The fingers are the magnetic field lines and the direction. So similar to what it would be on a straight line, a straight wire, except that the palm, you do open palm instead of curled fingers, and the palm is the magnetic force. Now you can think about it, this is how I remember it. If you push on someone, you have to use your palm, and you can't pull using your palm, it has to be a push. So that's how I remember the three different directions, and yeah, we always use left hand for negative, right hand for positive. So with this hand rule in mind, the magnitude of the force is given by this formula here. So Fm, which is the force magnetic, equals the Q and then the V perpendicular times B. So Q is the charge of the moving particle. F is obviously the force. V is the speed of the particle that is perpendicular to the magnetic field. So whatever component that is perpendicular, only that component. So to maximize the force, you have to have a velocity that is completely perpendicular for all of that velocity to actually take effect into the force. And then B is the magnetic field strength at that location, and that's measured in Teslas. No, not that Tesla, the other Tesla. Okay, so example 1 here, an alpha particle travels due west across the Earth's standard magnetic field lines. Which direction will the alpha particle be deflected? Okay, so an alpha particle is basically a particle that has two standard units of positive charge. Okay, so if it's traveling due west across the Earth, this is a top-down view, by the way, that we're going to look at now. Whoops, sorry about that. This is a top-down view that we're looking at. Okay, so it's traveling due west. By the way, never eat soggy wieners. That's how I remember it. So top-down view. It's traveling due west, so that's the velocity of the particle. Now, that's our velocity, but the Earth has standard magnetic field lines. So now we need to think about the globe of Earth, and you can go back 2 videos if you don't remember this, but the North Pole of the Earth is actually magnetically south. And the South Pole is actually magnetically north. So the field lines actually go from south to north. And so what that means is that our magnetic field lines are in this direction. So magnetic field. Okay, so since we know the path of the positive particle, first of all, it's positive particle, so we're going to use our right hand. And since we know the path of it, that's going to the left on the screen here. So we point our thumb to the left, and we use our fingertips pointing up on the screen or on the page. So when we do that, you can see that our palm is facing down, which means that the force is pushing the alpha particle towards the ground here. So it's going into the page. So this is the force direction that it's going to feel as it's traveling through the magnetic field. So the force is pushing it towards the Earth in this case. So towards the Earth, or the force is down, okay, towards the ground, right? Because this is a top-down view. Okay, so hopefully that helps a little bit, but now we're going to have a really complicated example question here that we're going to take a look at, or relatively complicated at least. A velocity selector is a device that only allows ions with certain velocities to pass through undeflected. This creates a beam of ions with all the same speed / kinetic energy at the end. The device uses an electric field perpendicular to a magnetic field to create opposing forces that are balanced. Gravity is minimal in this example. Okay, so P ions being deflected upwards, Q is being deflected down, D are not being deflected, having perfect velocity, and that means it has balanced magnetic and electric field strength. Okay, so assuming that each of the ions are all singularly ionized positive hydrogen ions, okay, so that means that they're going to be positive. We're using our right hand. Okay, right here, this means we're using our right hand. Now, because we're using our right hand and they're moving, the thumb points in the direction of their motion, while their motion is to the right. So that means that the the palm is pushing upwards. So if we look at a particle within there, maybe let's just do P. Okay, if we look at the particle P, I'm going to use different colors for it. If we look at the particle P, it has a very strong force, a magnetic force, because it is being deflected up, and it's being deflected up more than it's being deflected down. So that means its force electric is smaller than its force magnetic. We'll deal with that in a little bit when we're answering part A. But let's continue on to D. D, on the other hand, is not being deflected. So that means its force magnetic is equal to its force electric. Maybe I'll say that here. It's equal to the force electric. Whereas over here, force magnetic was greater than the force electric. Okay, and then the last one is Q, which has a greater force electric. Maybe I'll try to make it about the same size as all the rest, because that didn't change. But the magnetic field, the magnetic force, is less. So the magnetic is less than the electric in this example. So which of the ions have the greater velocity? Well, all we have to do is use the formula here. So F equals QVB. Now, we're not going to actually use the formula. We're just going to use it qualitatively for this, because it's not asking the value. Okay, but we do know that the force magnetic is greatest for the P particle. So if that's the greatest one and everything else stays the same, it's all the same positively charged ions, the magnetic field doesn't change. So that means that P has to have the biggest velocity. Okay, so we've drawn a free body diagram for D actually as well. That was part of answering the question for A. So we kind of did that already. But let's determine the speed of the ions. So for the D ions that we were actually balancing, hopefully you can see that we have F net equals MA equals all the forces added. And in this case, there's only those two forces, and this is 0. So it's going to look like this. And we did already have this before, but I did want to, just take our time to make sure we fully understand it. So Fm equals Fe. Now Fm is QVB equals, and then Fe is going to be our force electric. Now, we already know the electric field strength. It's given there. But there's this formula, F over Q equals E. So if we just move the Q over, F equals QE. This is the field strength, by the way. So then we can, instead of having Fe, right, we could have QE. So now we can solve for the speed of the ions, and you can actually see that the Q's are going to cancel. So we're going to have VB equals E. And now we can solve for V. So V equals E over B. E is the field strength, that's 500. B is the Tesla, which is 1.8 times 10 to the negative 3, so 0.0, that's 2, 3, and then 1, 8. Okay, so now you just need to plug that into your calculator. And we get the result of 2.7, we just want 2 sig digs, right? So actually 2.8 times 10 to the 5 meters per second. All right. So actually not too complicated of a question, but hopefully some of those free body diagrams helped you better understand this velocity selector device. I hope this video helps you understand moving charges in magnetic fields a little bit better. Good luck.